Hi guys, today let's discuss LeetCode question 23, merge case sorted linked list. So earlier, this is a very important question from the interview perspective, and this is categorized as a hard level question in the LeetCode. So this question is quite similar to the merge to sorted linked list. So that is already discussed in the earlier videos. So kindly check out that video as well. So let's go into this question. So in this question, if we go to the example one, so we are given k linked list in the form of a list. Here in the representative purpose, they have mentioned it as 145, but only in this list, there will be only the head of the linked list, which is the address of the one will be specified. And it is the same for the remaining two linked list as well. In this 134 linked list, only one is specified, and in this 2 and 2,6, only the head of this linked list, which is 2, is mentioned. So you can actually treat it as like a list of linked list nodes. But here the representation is like a list of lists, but the actual question is in the form of list of nodes, linked list nodes. Okay, and the output is like after merging all the values 145, 134, and 26, the output that we get is 1, 1, 2, 3, 4, 4, 5, 6. So the output we should return the output as the head of the linked list, which is a 1. So this is the output that has to be returned. So let's go to the example 2. In this example 2, we are not given any linked list nodes. So this is one of the corner case. And let's go to the example 3. In the example 3, the representation is like an empty list. So this representation means the head of the linked list is actually none. So this is also one of the edge case. So that is the difference between the example 2 and 3. Example 2 doesn't contain even the none value, but in the example 3 we have a none value. So let's go to the explanation part of it. Hi guys, let's go to the explanation part of it. So the input is 145, which is a linked list, and 134, that is also a linked list, and 2, 6. So the output is 1, 1, 2, 3, 4, 4, 5, 6. So the output we should return the head of this linked list, which is 1. So let's go to the brute force approach first and see what is the time complexity and how we are going to solve using the brute force approach. So first, let's take all the first values 1, 1, and 2. Let's determine which is the smallest of these values. So 1 is the smallest value, and we have taken the note of it. Then we move to the next. Then we compare 1, 2, and 4. Then we come to know that 1 is the smallest. Then we make note of it. And at each step, we move to the next pointer in this linked list. So what is the time complexity for this brute force approach? How are we going to do it? So considering there are there are k linked lists. So at each step, if we are going to find the smallest of all these k first elements in this linked list, so the brute force, the complexity will be like time complexity. So it is k into the number of elements. There are k linked list and into m. K into m. Here, length of the linked list is represented in the form of m. So this is the time complexity that we are going to use. And regarding the space complexity, we are not going to store any of these values. We are just computing the smallest value of all these k elements. So we are going to use a constant space, which is of 1. Okay, but there are better approaches in order to solve this problem. Let's look for the other solutions as well. So today I'm going to give 2 approaches. So both are using heap data structure. So in Python, it is implemented using the heap queue library. So optimized solution. So let's discuss both the approaches. approach 1, and approach 2. In both these approaches, we are going to use heap data structure, but the way we are going to use the heap data structure will be different in these two use cases. So in the first use case, what we are going to do is like we are going to create a heap data structure and we are going to store all the first elements inside the heap. We are just going to use, okay, let's discuss something about the heap data structure here as well. So heap data structure, we are going to use three methods. Okay, the first method is going to be heapify. This is for creating the heap. And the second one is heap push. These are the three methods that we are going to use. Heap push is like push a node into the heap. And the third is heap pop. This is for popping the node from the heap. So we are going to use these three. So what will be popped will be the smallest element. So in Python heapq library, it is implemented such that it is implemented like a min-heap. So which means when you are popping an element, by default, the minimum element from the heap will be returned as will be popped first. So it is called min-heap implementation. And we can do like max heap as well, but we have to use a small logic for that. That is not required for this question. So let's go now, after discussing this heap, let's go to this approach 1 and also approach 2. So what are we going to push into this heap? For this heap to work, we actually need the node. One is we need the node, and two is node val, and the third is the index, means which linked list this node actually belongs. So we are going to store these three information in the form of a tuple. So the information should be stored like this: node.val, index, node. Let's discuss why we need all these three information. Because as discussed below, the way the heap library works in Python is it is implemented for the min-heap. So in order to find the minimum of all the list nodes, in order for the heap to compute the smallest value, we need to specify, it needs to understand which is the smallest value. So that information is provided by node.value. So in this case, 1, 2, it knows like 1 is the smallest of all these elements, but there is a corner case. So one is like duplicated. So there are two ones. So which linked list needs to be taken first? Which needs to be popped first is the question. So in order to break the tie, we are going to take the index position. Since the index of this first one is 0, this is 1, and this is 2. First, this is the node that is going to be popped, and we are going to store that value here. So that is the reason we need to store node.value, index, and node. Because in order to eliminate that tie of the node values, we are using the index as well. And node, we are using it because we need to point to the next pointer. After the one is used, we are going to move to the second node. So that is the reason we need that information node as well, because that information will be lost when we are not storing it inside the heap. So what will be the time complexity of this one? So the time complexity of this one will be like, since when we are popping an element from the heap will realign itself to store the min value at the index position 0. So at each step it is going to be log k, and since there are k into m elements inside that linked list, it is going to be log k into m. So that is going to be the time complexity for the approach one, and the space complexity is going to be of the order, sorry, is going to be of the order k into m. The reason we are using k into m is because there are total k into m nodes in all k into m nodes in this k linked list. So for each of that storage in the heap, we are storing node value and also the index. So it is going to be of the order of the number of elements number of nodes in the linked list. So it is k into m. Okay, so this is clear. So can we do anything better than this heap? Yes, we can do better than the heap, but we are going to use the same implementation, but instead of storing node dot value, index and node inside the heap, we are going to store only node. What if we only store the node? Then obviously our space complexity will be much better, because then we'll be using only constant space. And the time complexity remains the same, because we are anyway going to construct a heap, so the time complexity remains the same. But the space complexity will be of 1. But how can we do using this storing just a node, and how this min-heap will understand what is the smallest of all these nodes is the question. So for this approach too, we are going to use operator overloading. Let's discuss this part in the coding exercise. Yeah, let's quickly code this up. Let's start the coding by importing the library. So from heap queue import. So we discussed heapify method, heap push, and heap pop. So we are going to import all the three. Then let's create a heap merge. So this is the heap data structure that we are going to use, heap merge. So the first step is to actually heapify. So it is like converting a normal list into a heap. So heapify, heap merge. So we have created an empty list, and then we are we are heapifying it, like creating a heap out of it. Then we are going to store all the first elements of all the k linked list in the heap. For node in lists if node is not none. So this is to solve the edge case. If the node is not none, only then we are going to store it in the form of in the heap. If node is not none, then what are we going to store in the heap? So heap push of heap merge, comma. Then we are going to store. Let's do the first approach first. So we are going to store three information in the form of a tuple. One is node.val, comma. Then we are going to store. Okay, we are going to store the index. Right. Let's store the index and also node information. Okay. So here we need the index of the node as well. So in range of length of lists for I in range of length of list, and if list of I is not none, heap dot, this is going to be node dot value, so it is lists of I dot val, comma I, comma, and this is going to be lists of I. So we stored all the first elements, and we have pushed all the first nodes of the linked list into the heap. Then we are going to create a dummy linked list node. So this is just for the ease of use. So we are going to create a linked list node which is 0. Then we are going to till this heap is empty, we are going to loop through this, and we are going to, at each step we are going to store the element uh, as a dummy.next. So we are create this dummy.next will actually store the merged the output, the final output. So while heap merge, then what are we going to do? We are going to heap pop. So let's do heap pop of heap merge. So we are going to get a pop node. So this pop node is essentially a tuple, just like the list. We are storing the 3 information in the tuple. So that is the output that is stored inside this pop node. Then what are we going to do? So then we are going to store this information. If pop node if pop node dot, okay, let's store this pop node. So dummy.next is equal to pop underscore node of 2. So the last the index 2 will actually store the node, and we are going to dummy.next is equal to that linked list node. And what are we going to do next? We are going to iterate to the next position. Dummy is equal to dummy.next. Then we should actually push this linked list also back onto the heap, but by updating that next node in the linked list. So how are we going to do that? Then we are going to use heap push again, the heap push. Then we are going to use the heap that we have created, heap merge, comma, and we have to store all the 3 values. The 3 values will be like pop underscore node of 2 dot next, and the other information is going to be the index. So which is going to be pop node of 1 comma, this is going to be pop node of 2 dot next dot val, and this is going to be pop underscore node of 2 dot next. We stored this, but there is an edge case here. So what if the next node is actually none? So we are going to do that. We are going to eliminate that edge case. So if pop node 2 dot next, only if there is, okay, let's be more clear, if is not none, then only do this heap push. Yeah, looks like I think we are done. So what should, okay, let's create one more reference pointer to this dummy. Result is equal to dummy. We have created one more reference for this. So we are essentially, we should return the next pointer of this result, because we have created an dummy node in the form of list node of 0. So we are going to result the next pointer of it. Okay, looks good. I think we can run the code. Let's run the code. Okay, I think it is successful. Let's quickly submit the code as well. Okay, so our runtime is 79 milliseconds. It beats 97%, and the space we are utilizing, as discussed in that earlier section, we are using like of k into m space. So in the next approach, we are going to optimize this one. So let's quickly copy this code. Okay, we have copied the code. So what are we going to change inside this? Let's quickly comment that above approach. So this is going to be approach 1. This is going to be approach 2. So what are we going to change in this approach 2? So instead of storing all this information, we are only going to store the node value in the heap. So we are not pushing all the 3 information in the form of a tuple. And when we are popping, we are getting only the node. So we are saying dummy.next is equal to pop node. Dummy is equal to dummy.next. And this is also going to be pop node.next. and here also it is going to be pop node of pop node dot next. So it is simple. Now comes the important step. How is the heap going to understand the smallest of the smallest node in the heap? So for this we are going to use the operator overloading. Let's create a dummy function. Define less than. We are going to overload the less than operator in the linked list in this list node. So we are going to create this temporary function less than, and we are going to store two values. One is like self comma other. So imagine like we are passing two objects inside this one. Then what are we going to return? If self dot value is less than or equal to other dot value, then we are actually returning true. Then we are saying that it is less than, like the first object is less than the second object. Okay, now we have wanted to do the overloading operation. So we are going to do this list node dot, so less than will be like underscore underscore lt underscore underscore. So we are going to overload inside this class list node class, this method is equal to less than. That's it. So we have overloaded this operator, and then when we are constructing the heap, we are storing all the nodes linked list nodes inside this. Then that heap data structure will understand how to find the minimum element and pop the minimum linked list node from the heap. Okay, I think we are done. Let's quickly run the code as well. Okay, we got an error. So it is saying like list node object is not subscriptable. Yes, we made a mistake here. Pop, it is not pop node 2.text. We are only storing the node, so it is pop node dot next. Let's run it again. Okay, it has passed, and let's quickly submit it as well. Yeah, if you see now, like the memory utilization, it beats 80.9%. So that is the optimization that we have done to optimize the space. Yeah, thanks for watching.